Hi, welcome to this lesson on 2D and 3D trigonometry, part 1. Let's have a look at question 1. We're given a semicircle, so half a circle, with center O, and we want to figure out angle AOC. So this is this angle here. So before I do that, because I have a semicircle, I like to put in as much information as I can first, and then from there, work out any problems I need to. So first of all, if O is the center, then I see three radius lines in this drawing. I see EO, I see OB, and I see OA. Okay? So those are all equal length. I also know that EB is the diameter of that semicircle. So this will imply then that angle EAB is 90 degrees, so this angle here. And that's from angles in a semicircle. So you can see we're using some theory from circle geometry within this trigonometry problem. So that's what mathematics is all about. Taking different areas within mathematics and combining them to use their true power to problem solve. Okay. So now I know that because EO equals OA, okay, equal radii, this implies then that triangle EOA is isosceles. Okay, so this further implies then that angle OAE, this angle here, must be theta as well. Okay, so the isosceles triangle. So now I can solve for angle AOC in two different ways. So the first way I could say is that angle AOC is equal to theta plus theta, which is 2 theta. And that is from exterior angle, this angle here, is equal to the sum of the interior opposite angles. Okay, so if I go into the interior of this triangle, then the opposite angles are those two there. Alternatively, what I could have done is we could have said that in triangle EOA, we have theta plus theta, so this angle plus that angle, plus angle EOA must equal 180 degrees. And that is from angles in a triangle. Okay, that must sum up to 180. So therefore I have 2 theta plus this angle is 180 degrees. So angle EOA is equal to 180 degrees minus 2 theta. So that's this angle here. Therefore, I can say that angle AOC plus angle EOA must be 180 degrees. Okay, so this entire angle here, and that's from angles on a straight line, because that diameter EOCB is a straight line. So therefore, angle AOC equals 180 degrees minus this angle EOA, which we worked out to be 180 degrees minus 2 theta. And if we expand out that minus sign, we're left with 2 theta. Okay, so those are the two ways we could have solved for angle AOC. So next we want to determine an expression for cos theta using triangle ABE. Okay, so triangle ABE is this larger triangle in the circle. So what I like to do is, if I'm focusing on a triangle, I like to sketch it out. Okay, so let's draw that triangle here. So we know that's 90 degrees from angles in a semicircle. All right. Okay, yeah, just double checking, yeah, okay. So yeah, we got this 90 degrees minus theta as well. That's just from within this bigger triangle here. Okay, because we know it's a 90 and we were given it this theta, then by angles in a triangle, this must be 90 minus theta. Okay. So we've got all that information. So cos theta, so here's the theta in this triangle. So cos of theta, by our trigonometric ratios, is the adjacent side over the hypotenuse. Hypotenuse always being opposite the 90 degree. So in that case, this is going to be EA divided by EB. So that is an expression for cos theta within that triangle. All right. Next, we want to determine sine theta in triangle ACE. So where's triangle ACE? Is this one here. So we know this was given as theta, and because AC is perpendicular to EB, which is given in the diagram, therefore this angle must also be 90 degrees by angles on a straight line. Okay, so sine theta is going to be opposite over the hypotenuse. So sine theta, that's equal to AC, right, over EA. So that is the expression for sine theta within that given triangle. Now we want to determine the expression for sine 2 theta using triangle ACO. So triangle ACO is this one here. Okay, but we worked out this angle to be 2 theta in the first question. So that's 2 theta, and we know that this is a 90-degree angle because AC is perpendicular to EB. Okay, so sine of 2 theta is going to be opposite side over the hypotenuse. So that's going to be AC over AO. Okay? And then lastly, using the results of the previous questions, show that sine 2 theta is equal to 2 sine theta cos theta. So these are the famous trig double angle formulae. So now we can actually prove it using this geometrical argument that we've constructed. So we've seen the algebraic proof of it. So this is a nice geometrical proof of it. Okay, so sine of 2 theta, we worked that out in the previous question. That was AC over AO. Then sine theta, we worked out earlier, that was AC over EA. And then lastly, cos theta, we worked out, was EA over EB. Okay, so putting all this information together, let's see what we have. So on the right-hand side, 2 sine theta cos theta. If I replace that with the expressions that we created, that's 2 times AC over EA times EA over EB. So now the EAs will divide into each other, okay, because EA is a length and it's a non-zero length, so I can divide it out. And that's 2 times AC all divided by EB. Okay, but we wanted to get to this, AC over AO. Then we've shown equality. So now let's look at what we have. AC is this line here, and EB is this entire line here, the diameter. But the diameter, we know, is 2 times the radius. So it's 2AC divided by 2 times the radius. But which radius length am I going to choose? Because there's 3 of them I can choose. EO, OA, or OB. But can you see in this expression here, we have AO. So let's use AO as the radius length in this question. Okay, so now the 2's will divide each other out, and we're left with AC over AO. But that's exactly equal to sine 2 theta in the given expression that we created. So therefore, geometrically, what we've proven here is the sine double angle formulae, which I think is really cool from a geometrical standpoint. Okay, so we have a geometric and an algebraic proof for this. Awesome. I'll see you in the next one.